All right, so we're live right now. Here are the things that I'll do today, folks. I'll go over the key parts that will be on the test. Namely, I'll go over antiderivatives, the use of the fundamental theorem of calculus, and uh, and then substitutions. There's All right. There's somebody else joined. Okay, so uh, there's a focus on these three topics, as I was telling you, just because they are going to be the ones that you will see in calculus 2 over and over again. In fact, in calculus 2, you are going to start with these types of substitution problems. So by substitution, I mean integration by substitution. So calculating antiderivatives by substitution, and these. So I tell you, these are really really important. So I'm gonna get started here with some. I have selected some problems. Of course, if you want to ask a question, if you want to see how a certain problem is done, let's say from the selected problems for the test, the ones that I posted out there, the practice problems. Of course, we can certainly do one of those or a few of those if you wanna start that way. In any case, the ones that I selected are very much like those, or so from either from that set or very much like those. All right, so let's get started. If you have any questions again at any time, just type in the chat or just open up your mic and turn on your mic and speak up here. So I'm going to start with antiderivatives. So one of the sections you want to focus on is 3.9, and that's antiderivatives. All right. Well, I forgot to reset this pen, so let me just 1 second, folks. I apologize. Format. Okay, so let's do this format. Antiderivatives. All right, so we are going to do problems like there we go. So got the thicker format problems like well, I'm going to start with some easy ones. Again, we've done this before in some other sections. This is just a collection of interesting problems. So one from 3.9 will be fairly easy. The question is, you got f of x equal to 4x plus 7. Do the antiderivative. So antiderivative, remember what I'm going to do now, I'm just going to write the symbol for the antiderivative is this 4x plus 7 dx. And we know that the antiderivative goes like this. So for 4x, you have 4 times 1/2 x squared. Then for 7, you have 7 times x. So the answer here is when you simplify 2x squared plus 7x plus a constant. I'm not going to worry much about that constant. So again, if you forget the constant, it's not a big deal in Calc 1. All right, so that is the answer. So be careful. Again, the type of problem that you see here is simple powers of x. Now, on the test, you would also see some more complex types of powers of x, like this one, number 7. I selected 7 here from 3.9. And that is f of x equals, and over here it says 7x to the 2/5 plus 8x to the negative 4/5. All right, so how do you do the antiderivative of this one? whether the problem says find the antiderivative like that with words, or it's simply asking you to evaluate the integral equivalently, evaluate the integral 7x to the 2/5 plus 8x to the negative 4/5 dx, if this is what you want to do. It's the same thing. So so it boils down to the same thing. And the first part here, 7x to the 2/5 is 7 times. Let me just delete that here first. So before I do, yeah, so it's going to be 7 times. X to the 2/5. First of all, I take care of the exponent is going to be 2/5 plus 1, which ends up being 7/5. And then over here we have times 5/7. So it's 7 times 5, 7 times that. Plus, and the next thing here is 8x to the negative 4/5. So the antiderivative will be 8x to the negative 4/5 plus 1 is 1/5. And then 5 over 1. So so all of that will be 5 x to the 7/5 plus 40 x to the 1/5. So so this is going to be the antiderivative. That's then plus a constancy. All right, folks. So you will see easier problems like this, and you will see some more complex ones where you have fractional exponents. And don't be afraid of these. These are the exact same types of problems. You just, you know, the same mechanics work. So you just add 1 to the exponent and then flip over the exponent in front of a new result. So in this case, for 7x to the 2/5, the constant stays there, 7 outside. But then the thing is x to the 7/5 and then 5/7. All right, so that's going to be that. The next thing that I'm going to do here is something with some square roots, and that's going to be number 12 of section 3.9, of course. So we want to do the antiderivative of f of x equal to, and I'm going to write f of x here, the cube root of x squared plus x square root of x. All right, folks. So this is gonna be we need to rewrite this. This is one of the problems when we need to do some prep work before we actually do the problem. So the function f of x itself, again, this is prep work. The function f of x itself is simply x to the, so cube root of x squared is x to the 2/3 plus, so remember that from, this is kind of one of those things that you need from college algebra or pre-calculus. So remember how to operate with exponents like this. This is a must because you'll end up doing things that are more complex than this in Calc 2. And then the next thing here is x to the first times the square root of x, which is x to the 1/2. 1 plus 1/2, the exponent will be 3/2. All right, so this is the function that I want to find the antiderivative of. And now the problem is to calculate antiderivative. So we're looking at the antiderivative of x to the 2/3 plus x to the 3/2 dx. That's going to be, folks, all right, so for x to the 2/3, we have x to the 5/3 antiderivative because it's adding 1 and 3/5 in front of that. Plus, and for x to the 3/2 is x to the 5/2 and then 2/5 in front of that. So, so this is the antiderivative, and the result of it is, you know, you can say plus c here if you want. So this is the answer. But I want to point out that you can rewrite this, so you don't have to, but you might see this rewritten as, and maybe one of the options would be something like this. over here you have the third root. So everything that's in the denominator becomes the index of a root, the third root of x to the fifth plus, and the next thing is 2/5 times the square root here. So we don't write the 2 here when it's a square root of x to the fifth plus c. So this could be a possible way to write the exact same answer. So again, I'm not particularly concerned about these things, but again, they do appear in Cal 2, so I want you to kind of be on top of things. So again, pay attention when you convert from these square roots to, or cube roots or so, to fractional exponents. That's all I'm gonna say. All right, and then there's problems like these. So I'll do 2 more problems, and we will be all set. So there's problems like from this section, that is, we will be all set. So problems like number 15 of section 3.9, and let me copy the problem very quickly. F of x is equal to, there's a fraction, 1 plus t squared divided by the square root of t. So this is a fraction, and this is equal to 1 over square root of t, which is t to the negative 1/2, plus t over square root of t, that's t to the 1/2, plus t squared over square root of t, which is, all right, t to the 2 minus 1/2, or 3/2. All right, folks. So now, how did I get this thing again? This is so again, prep work, right? Very important here to write a bunch of powers of x. Well, here's how I did that. I did this, folks. 1 plus t squared times t to the negative 1/2. Instead of 1 over square root of t, I would say t to the negative 1/2. And when you do the product, you will see that you get exactly that, because look here, 1 times t to the negative 1/2 is that, t times t to the negative 1/2 is t to the first here, really. So, oops, doesn't work. All right, so the power here is 1 minus 1/2. It turns out to be 1/2, and then 2 minus 1/2 turns out to be 3/2. So this is the thing that we are working on here. All right, now we want to do an antiderivative. In other words, you want to do the antiderivative of t to the, oops, sorry about that. T to the negative 1/2 plus t to the 1/2 plus t to the 3/2 dt. So we want to do the antiderivative of that. And this is going to be, so again, we go term by term at this point in time. T to the negative 1/2 has an antiderivative of negative 1/2 plus 1, which is 1/2 times 2. Plus t to the 1/2 has an antiderivative of 3/2 times 2/3. And then t to the 3/2 has an antiderivative of 5/2. When you add up 1 and then times 2/5. All right, so this is the antiderivative, and you say plus c. That's the final answer. I'm not going to worry much about rewriting this yet again as a bunch of square roots. I think this is good enough. So over here, this is the answer. All right, so this is number 15, and again, I'm going to go to number, the next thing, the one I selected was number 17. So let's do that. Number 17 here, there could be, from 3.9, f of, I'm going to change notation a little bit. I'm going to use t instead of theta. F of t equals 2 sine t minus secant squared. Now, the reason why I'm using t is I don't necessarily like the Greek letter theta. So in the book, they have theta instead of t, but that's the exact same problem. So, so to find an antiderivative you'll have to do the integral of 2 sine t minus secant squared t dt. And we know how that goes. For sine t, the antiderivative is negative cosine t. So this is going to be negative 2 cosine t. You got to learn those trigonometric antiderivatives, right? For sine, negative cosine. For secant squared, in this case, is tangent. Tangent t. Kind of came up here. So let's put a nice t here. So tangent of t, that's going to be the antiderivative here, and plus c. This is the antiderivative. All right. So these are the types of problems I would want to insist from this particular section. Now, as I said, I put some questions in the practice with some questions where you calculate the area under a graph and things like that. I'm gonna review those a little towards the end of the hour. Now, what I'll do now, I'll do the fundamental theorem of calculus because I said that's very important. Okay, what are the problems? I missed the problems here. Oh, okay. So, so look at as I said in the homework, I'm going to put a focus on just the computational aspects of those. So, so when you calculate things like, and I'm going to do a couple of problems from here, things like this. Let's say this is number 23 of section 4.3. And I'll do the integral from 1 to 9 of the square root of x dx. All right, so when you see an integral like that, remember, folks, what you want to do, you want to rewrite the function here. So do some prep work. So this is prep work here. So this is going to be integral from 1 to 9. And that's going to be x to the 1/2, right, dx. And at this point in time, you are working with this x to the 1/2, and that's the one that you want to calculate the antiderivative for, folks. So, so antiderivative, we do the integral of x to the 1/2 dx. And this is going to be equal to, we all know what that is, right? So is x to the 3/2 over here times 2/3. That's simple. We don't need a constant. See, as I said, we just take that and we substitute and we get the numbers here. So so this is going to be, we take that here, which is going to end up being 2/3 times 9 to the 3/2. So we substitute 9 first, right? And then we substitute 1 in the formula here. So minus 2/3 times 1 to the 3/2. And that ends up being, folks, all right, so 2/3. Now, 9 to the 3/2 is easy to evaluate, actually, is 9 to the 1/2 cubed. 9 to the 1/2 is square root of 9 or 3. So, so that's going to be 3 cubed or 27 over here minus 2/3 times 1. So, so this is going to end up being 2 times 27 over 3. That cancels out a little bit here. So 18 minus 2/3. So, so it's going to be 17 and 1/3 if you want. All right. Or if you want to put a fraction with just 3 in the denominator, 21, 52 over 3. That's the final result. All right, so regardless, that's not so important. The important thing is the process here. So, so again, folks, remember, when you calculate a definite integral, it really boils down to doing the antiderivative properly and then substituting the values, the bounds of this integral in the formula for the antiderivative. So I'm going to do one more. There's nothing really intelligent beyond that when it comes to these things here. So, so I'm going to do another one. Again, all these functions, the difficulty, you know, the weight, the main weight lifting is done by the antiderivative, not by the definite integral. The bounds, you know, they play a marginal role in a way. They play a role, but that's not the key role here. So number 25 of section 4.3. And I'll tell you the reason why I'm doing this. So it's integral from pi over 6 to pi of sine theta d theta. Well, we still ended up using theta here, so that's okay. All right, folks. So the reason why I'm doing this, again, it boils down to an antiderivative. We know how to handle that. The reason why I'm doing this is to review some values of the trig functions at important values like this of pi over 6, pi and so on. So these can be done in Desmos, but pay attention when you calculate in Desmos. Make sure, I'm not sure if it even gives you square roots and things like that, but make sure that you set your thing in radians there, because otherwise, pi over 6 is the measure in radians is not the same as the one in degrees. So it's gonna mix things up there. So in this case, what I need to do, I need to do the antiderivative of sine theta d theta, which is the antiderivative of sine is negative cosine. And we need to do that, evaluate that from pi to pi over 6. So this number is going to be negative cosine of pi, yeah, minus negative cosine of pi over 6. And this is going to end up being negative, cosine of pi is -1, so negative 1 is 1, plus, and then minus cosine of pi over 6. Now, cosine of pi over 6, everybody should know that is going to be square root of 3 over 2, so 1 plus square root of 3 over 2. So this is the final answer. Again, Desmos doesn't quite give you this. I mean, you can check that this is the final answer, but you really have to evaluate the cube root of a square root of 2. I'm going to do that quickly with Desmos to see what's going on, see the difference. I'm going to share with you this thing here. So this is, that's not the one you want to see. All right, so I'm gonna do Desmos. All right. So folks, okay, so we do integral, we said, pi over 6 here, and pi over here. Oops. All right, and we, what did we have? We had, let's put a pair of parentheses here, dx, and let's put sine, oops, sin sine x. All right, then it gives you this number here, but then do you know what that number is? Let's see. So what we got in our calculations here was 1 plus square root of 3 over 2. So let's see if the same number is there. So if we calculate 1 plus square root of 3 over 2, 1 plus square root of 3, all of that divided by 2, there we go. So it's the exact same number. So you see, you still need to know the values of the trig functions to at least check that the answer is correct. So this type of answer would not be acceptable on the test, rather this one here, if I put the specific values of the trig functions. You can actually calculate these, but again, you need to review some of these values of the trig functions. That's what I wanted to say. All right, so again, not many of them. So review, just review here, folks. Sine 0, just now let me actually write them down because it's easier to write them down. Sine 0 equals 0. Sine of pi over 3. Sine of pi over 6. Let's put pi over 6 first. Sine of pi over 6 is 1 over 2. Sine of pi over 3 is square root of 3 over 2. Sine of, what do we have? Oh, sine of pi over 4. So, yeah, hang on a second, folks. So let's put sine of pi over 4 first. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 3, we just wrote that, square root of 3 over 2. And then sine of pi over 2 is 1. So these are the values of sine. The values of cosine goes exactly opposite. So, so if the values of sine are 0, 1/2, the square root of 2, square root of 3, square root of 1, the values of cosine go exactly opposite. So you start cosine of pi over 2 is 0. So you start with the last angle here. And the one before that was cosine of pi over 3, which, so we got 0 from here. It turns out to be 1/2 cosine of pi over 4, which turns out to be square root of 2 over 2, cosine of pi over 6, which turns out to be 1/2, and cosine of I'm sorry, nope, not 1/2. Pi over 6 is square root of 3 over 2. All right, and cosine of 0, which ends up being 1. So so these are the values of cosine. Also remember that tangent of pi over 4 is 1. So these are more or less all the trig values that you would need to use. You may take notes here, so you can use these. Just remember that at some point you would have to have them memorized. But I don't expect you to have them all memorized, so so at least know where to look for them. All right, so so that takes care of fundamental theorem of calculus, and finally we're gonna spend some time on doing some substitutions. As I was, and that's then if we have time, we'll do some areas under curves. If not, that remains, it's a simple topic for you to review. So, so as I was saying, substitutions in indefinite integral boil down to two types of, there's two types, type 1 and type 2. For these substitutions, and type 1 would be an antiderivative of a function like this. So power of some function times the derivative. So that's one type. So a power and then times the derivative of whatever this function is involved here in the power. And number 2 is a trig function of, so if this is power of something, a trig function of something, and then times the derivative. So so these are all the types that we address in calculus 1. There could be some trickier problems, you know, when you don't quite see that you have to break up a problem into two, where you would recognize that, that maybe both types combined and stuff like that. But we didn't do many of those. So so if you focus on these and you understand these, then you will be able to tell what the other ones are. And also just to be aware that in calculus 2, you will learn many more types of such things. So in fact, I think at least three or four more times types. So so the first example is the one in number 7 of section. And these are illustrative problems. It's very intentionally listed like that because they reflect the two types of problems. This is section 4.5. And this is, so it's going to be integral. So they want us to calculate the integral of x square root of 1 minus x squared dx. All right. So let's recognize the type of a problem first, folks. Let's recognize power times derivative. It's fairly obvious that it's a power because of this radical here. So so let's move things around a little bit. So instead of square root of that, I'll say 1 minus x squared to the 1/2, right? And then we're gonna say times x dx. All right, and this is going to be equal to, so now we have a power, so the substitution goes as follows. the one that's involved in the power is 1 minus x squared. That's going to be u. We calculate du, which is negative 2x dx. And we are going to substitute. So this is going to be equal, well, over here we have u to the 1/2 times. And instead of x dx, we're going to divide by that. So it's going to be times negative 1/2 du. And this is the function whose everything is in u. Antiderivative here is going to be that negative 1/2 times u. The antiderivative of this guy is u to the 3/2 times 2/3. And altogether, this is going to be, it's going to cancel out a little bit here, and you're going to get 1/3, negative 1/3, I'm sorry, u to the 3/2, but u itself was 1 minus x squared, so you'll have 1 minus x squared to the 3/2. Okay, so this is going to be the calculation that we're looking at. Now this thing here is going to be the following. It's going to be the antiderivative. That's the final answer. If you want to add, I forgot the constant c. Well, yeah, you can add a constant c, but that's not so relevant. So that's going to be the key thing that I want you to figure out. So figure out the type of the problem and figure out the corresponding substitution property. So that's one type of problem. The second type of problem here is something like number, and I told you is number 8. That's the second type of problem of section 4.5. There's the integral of x squared sine of x cubed. So this is almost a gimme. Once you have a trig function, you see the trig function here. What you want to do, you want to separate. So you put the trig function on one side, sine of x cubed times x squared dx. And notice how u is equal to x cubed would be, so the thing here, that the one that's the argument of a trig function, that's going to be your substitution. Du, the derivative of that is going to be 3x squared, folks, dx, right? So don't forget to do the dx here because you'll have to solve for that. And we will see that, we see that the substitution here is sine u times, and instead of x squared dx, we will do 1/3 du. So we'll put that there, and that then it's straightforward. The 1/3 is there, and then sine u, the antiderivative of that is negative cosine u. Or if you want, negative 1/3 cosine of, now u is x cubed. All right, and that's pretty much the answer to our problem. All right, folks. So this is the answer to the question that was asked there. The other questions that I put out there for practice are just that practice problem. So I'm not. I don't think there's anything particularly new. These are the two types that I'm going to test. All right, and finally, let's do an example where we would need a substitution in a definite integral. So in a definite integral, let's do something like this. I'm going to choose numbers 37, correspondingly 38. And these two will reflect the two types of problems, this time around wrapped up in a definite integral. So 37 is from 4.5 is the following. So it's an integral from 0 to 1. the cube root of 1 plus 7x dx. As you can see here, this is the integral from 0 to 1 plus 7x to the 1/3. And this thing here is, well, so the antiderivative of 1 plus 7x to the 1/3 dx is going to be equal to, so we're going to add up 1 here. So when you do the antiderivative, folks, you need to make a substitution. But in this case, a substitution is visible. So u is 1 plus 7x, and it's almost obvious what we're going to do. We're going to do u to the 4/3. We're going to add up in the exponent here. Du turns out to be 7 dx. So this becomes really, in the first instance, we're going to replace u there. So u to the 1/3 times. And then instead of dx, we're going to say 1/7 du. So this is going to be equal to 1/7 times u to the 1/3. Okay, so u to the 1/3, the antiderivative of that will be u to the 4/3 times 3/4 plus a constant c. So that's going to be the result, and that's going to be 3/28 times, and you remember it was 1 plus 7x. So 1 plus 7x will be to the 4/3. So these, folks, is the antiderivative. We said we don't need that constant c. Why did I put that there? Okay, so this is the antiderivative. Now, with this antiderivative, we still have to calculate the integral. So this is what we're going to take, and we're going to substitute in here. Luckily, this is fairly easy because it's 3/28 times 1 plus 7x to the 4/3. So it will be 1 plus 7, 8 to the 4/3 minus, and then we're going to substitute 0 in the formula. So that's going to be 3/28 times 1 to the 4/3. So that's just that. All right, now 8 to the 4/3, luckily that calculates easily because it's 8 to the 1/3, which is 2 to the 4, so that's going to be 16. So it's 3 times 16 minus 3, that's going to be 3 times 15, or 45/28. All right, so this is going to be the answer to this particular problem when you do the calculation. So this is one type of problem when you do need the substitution, and then you do need what we do here, by the way, folks, is the fundamental theorem of calculus. I think you recognize that. And finally, we're going to do one more problem, and that's going to be problem 38, I said, which reflects the other type. So 38 of 4.5. Integral from 0 to square root of pi, x cosine of x squared dx. All right, so this is yet another. So this is all right. So let's calculate directly the antiderivative of x cosine of x squared dx, and that's going to be easy. Again, we recognize the trig thing here. The function is x squared. U equals x squared. Du is 2x dx. So when we do these things, we're gonna go here and we're gonna say integral from and I'm gonna write here, cosine of u because of x squared here. Now remember, x and dx are together here, so and you can solve for that, and it's 1/2 du. So this is going to be the antiderivative of cosine u 1/2 du, which is 1/2 times the antiderivative of cosine being sine. So 1/2 sine of x squared. Now the calculation is going to be this thing where you substitute square root of pi and 0. Luckily, you get 1/2 sine of pi, right? Square root of pi squared is pi, minus 1/2 sine 0. And we saw that both of these numbers are 0. So this then ends up being 0. This is something that you could do with Desmos. I'm pretty sure Desmos will get that. In fact, we'll check that quickly with Desmos, and that's going to be our last thing here. So so let's share that. 1 second, folks. New share. Let's Desmos. What is Desmos? All right. So we have this. All right. So in Desmos we can certainly calculate the integral from, and we say here 0 to square root of pi. 0 to square root of pi. All right. Make sure that you put that parenthesis thing because it doesn't like it otherwise. X cosine x squared. Oops. Okay. I have a problem here. So put parentheses again. Dx before you do anything here. X cosine of x squared. All right, and there we go. Voila, it's all 0. So it tells us here it is 0. All right, folks. So so this is the calculation done in Desmos. Now I am going to stop the review here. Again, do look yourself at calculations of areas. Areas under the graph. Actually, let me do one quickly here because we have time. So let's do one quickly here. So let's say, all right. So let's do a function quickly here. So so very quickly here, folks. I'm gonna do this one. So so I have this this graph in number 2 of section 4.3, and we have this function. So so the graph looks like this. So no, I'm just going to do very quickly here. Oops, not very straight, but you get the idea. So let me do that with red. Oops, come on, give me red here. Okay. All right, so I have red, so I go down like this with a line, and I go up somewhere here, and then I go down with something like this. All right, so so these numbers here are 1 and 2 here, and 3 here, and there's 4, there's 5, there's 6 over here. So not not very well scaled, but you get the idea. And then there's 7 over here. All right, so he says here, evaluate g of x. Well, g of x here, folks, the function g of x is integral from 0 to x of f of t dt. So he says evaluate g of 0, g of 1, g of 2, g of 3, g of 4, g of 5, and g of 6. Evaluate all of these numbers. I'm going to do just a couple of them. So g of 0 will be integral. This one here is integral from 0 to 0 of f of t dt. So that means 0. It's just the area under 0 here. So so there's no area. It's just a point here. There's no interval. G of 1 is the integral from 0 to 1 of g of t dt. That would be the area under this graph here. So that's g of 1, and that's going to be, this is a triangle, half of a square of side 1. So that's going to be 1/2. G of 2 is going to be integral from 0 to 2 of g of t dt. Now, if you look here, you would have this area with plus, but then you would have this area over here with minus. When you add them up, remember these are signed area, so this is going to be 0. Very easy to say. G of 3. I mean, I'm sorry, I said g of t here for whatever reason. That should have been all f's here. That's f. All right, so so that's f of t. That's f of t. This is the graph of y equals f of t dt. They don't need that dt here. All right, so folks, g of 3. That's an integral from 0 to 3 of f of t dt. And that ends up being, that area cancels this area, but then this area here, which is -1/2. And finally, you can do the exact same thing. G of 4 will end up being 0. G of 5 will end up being whatever this area is left over here because the other one's canceled out, and so on. All right, folks. I'm done for today, so I'll stop the recording here. You have a complete review. Now, please do work out these problems. If you want, when you watch the review, maybe you wanna stop the video where the problems are, work them out yourself, and then figure out the problems like I did them here.